When we talk about measurements, keep in mind a lot of what we're discussing here relates to how we deal with measurements in the real world. When you get out into lab, even out in the industry, you need to be aware that the way we measure things often affects the values. It can affect the values in your lab, in your factory. It can affect when you order supplies, what vendor you want to use, what supplier you want to use. Some scales are more precise than others. This shows two sets of scales. This one is precise to the nearest hundredth of a gram. This one is precise to the nearest 10,000th of a gram. So the scales that we use will determine how precisely or how accurately our measurements are being made. So to that end, we need to actually discuss significant figures. Significant figures, I know people have learned these in the past sometimes, have memorized the rules. But again, I want you to understand why we deal with significant figures, why we need to use them. And this is the reason, because we need to really let people know how precisely was a value measured. If someone used a very crude set of scales or a very precise set of scales, that can make a really big difference. When you order supplies from somebody, the purity of the sample will depend on the significant figures. If you go to the gas station to buy gas, you want to make sure that you're actually getting a gallon of gas when you pay for a gallon of gas. If they only actually measured gallons to one significant figure of precision, and you get 10 gallons of gas, you might only get half that. Even though the reading says 10 gallons, if the meter is very, very imprecise, then you might only get 5 gallons when you paid for 10. If you have a very precise reading, then you might be off by a little bit, but you might get 9.995 gallons instead, but you're getting more of what you want. So the precision makes a big difference when dealing with significant figures. So the rules we need to understand. Significant figures, basically we use all digits with known certainty, and we have one estimated digit past there. And I'll show you examples of what that how that comes about in real life when using rulers and analog measurements. For counting sig figs, all non-zero digits are significant. The zeros are what becomes tricky. Zeros depend on where they come into play. Leading zeros to the left, never count. They're never significant. Captive zeros that are stuck between two non-zero digits, are always significant. Trailing zeros, basically this is the definition I use, are significant if there's a decimal point somewhere in your value. And I'll go through some examples to help this make more sense. Then there are things called exact numbers, and I'll touch on those also. Non-zero integers, again, these are always significant. 283 has 3 sig figs. 7.315 has 4 sig figs. Leading zero. So again, these zeros do not count. Doesn't matter at all. Now, one thing that I don't like with this is I like to have units after this. I meant to change this when I did the slide, like grams and grams, or meters or grams or something else, to remind you that we're dealing with actually taking measurements. There's a reason we use the sig figs. If it weren't actually taking a real measurement, they wouldn't matter. So this is really telling me that I'm taking measurements using different types of equipment. In this first case, this equipment we use is only precise to the nearest gram, where this is precise to the nearest thousandth of a gram. So it tells people so people know how precisely was that value measured. So anyway, leading zeros here never count. Because I could have written this as 39 point, it doesn't like my decimals. Come on back there. 39.2 milligrams. It'll be the same exact mass, I'm just using different units. So the leading zeros never count. Well, they just sort of go with whatever unit we're using. But it's the same mass. If I've got a sample of lead, whether it's 0.0392 grams or 39.2 milligrams, it's the exact same mass. So, all right, trailing zeros, didn't have a cap to zero there. Meant to include one there. Anyway, trailing zeros are not significant unless there's a decimal somewhere in the number. 600 only has 1 sig fig. There's no decimal. 30 on the other hand has 5 because there's a decimal to show me that this was measured to 5 sig figs, to the thousandth place of whatever my unit is. As I said, captive zeros, zeros between two non-zeros are always significant, so we have 4 sig figs here. And then there are what are called exact numbers. Exact numbers are things that are defined and have as many sig figs as you need, which I think trips people up sometimes. I'll give a few more examples too. In this case, I would suggest maybe you pause the video, do these yourself to make sure that you have a handle on this. I'll give you a few more in a second. All right, so assuming you've already done these, this has 3 sig figs, this has 2, this has 4, and this also has 4. Rounding off, this is debatable. The book says this. I'm not that critical on rounding off only at the end of calculations, dropping insignificant digits. A long time ago, before the invent of calculators, all people rounded off at the same time. Every step of a calculation, you rounded off and proceeded on. And so everyone got the exact same number. But now with calculators, people round off at different stages. You can actually have part of an answer, take that to use for a different answer. So you can argue, where do you round off? So you can be off by a little bit. In the last sig fig, you might be off by a little bit from the textbook, for example. Don't be concerned about that. If you're worried about it, let me know. We'll go over it in detail to make sure you did everything correctly. Weakest link principle is the way the text is trying to decide what do we do when we do calculations. With sig figs, with numbers, hopefully you have a better handle on that. But when doing calculations, significant figures also impact our final result, whether we're adding, subtracting, multiplying, or dividing. And we need to decide what is going to impart the most error into our measurement. That's really what we're doing. Multiplication and division are fairly easy. Number of sig figs in the result basically is the same as the number of sig figs in the initial value with the least number of sig figs. And now it sounds kind of awkward, but basically, in the first calculation, we have one number with 3 sig figs, one with 2. The one with 2 is the least precise. It has the most error in it, the most percent error. Since they're multiplied, our final answer will only have 2 sig figs. Here we have one number with 4 sig figs, one number with 3. Percentage-wise, the one with 3 sig figs has more percent error, so therefore our final answer can only have 3 sig figs of precision. Fairly straightforward, fairly easy to get a handle on. Addition is a little bit trickier for people in many cases. Now I'll show you another example of this I think that will help you understand this better. In adding and subtracting, sig figs depend on the number of decimal places. Well, that's what I don't like the way the text says that. But it really depends on the precision in the least precise measurement. If you look at it this way, these two numbers, this number is measured to the nearest tenth of a gram. This number is measured to the nearest thousandth of a gram. Back there. Therefore, this number is off by plus or minus 0.05 grams. There's a lot of error here. And because of that, these last two digits here don't mean anything because they're going to get messed up when we add these two masses together to get a total mass. The error in this first measurement is going to swamp the precision in the second measurement. So our final answer is only good to the nearest tenth of a gram. So basically, we had one set of scales to the 10th gram precision, one set of scales to a thousandth of a gram precision. But the 10th of a gram precision is what's going to affect our final result. When doing addition and subtraction, depending on where you have parentheses, this really is implying that parentheses are here. So we would do the subtraction first, then do the division. In this case, we need to round this off to the appropriate sig figs. We'll suggest you do this for yourself, and then we'll go through the answers in just a second. So pause the video. All right, if you've done that, if you add these two together, you'll find out that this is going to have 3 sig figs because you'll get 1.7, actually 1.80, because this is going to have to be rounded off when you add them together. So you have 3 sig figs on the top, you have 5 sig figs on the bottom. Your final answer can only have 3 sig figs. So you need to round off to 3 sig figs of precision. Before going on to accuracy and precision, let me just do a few more examples just to show you. Again, do these yourself, pause the video, and then we'll go through these. Alright, this one has 3 sig figs. This one has 4. Trap 0, this one has 5. Again, this is the one, this has 1 sig fig. And now we put the decimal point over here, and people think, well, why does it magically now has to have 3 sig figs? Again, go back to, these deal with actually taking real measurements. In the first case with 200 milligram sample, we used a set of scales that was not very precise. So we only know that it's precise to the nearest 100 milligrams. The second 200 milligrams was measured with a different set of scales. That's more precise to the nearest milligram. So now we show the decimal point. It really shows people how precisely was that value measured. And keep in mind, most calculators do not do sig figs, so don't trust that to take care of your sig figs for you. Next case, 2.000 millimeters. This has 4 sig figs. Because we have trailing zeros with 0.0035 kilometers. We have leading zeros. Now this only has 2 sig figs. In fact, again, this number I could rewrite as 3.5 meters, which makes it easier to see why we have 2 sig figs here. So the leading zeros really depend on the prefix for our units. So that's why they don't account for our significant figures. 300 nanoseconds has 3 sig figs, so pretty basic. This value, work it out. You should be able to multiply this out yourself. I'm going to do that myself too. As far as significant figures go, though, everything's multiplied and divided. There's no addition and subtraction. So we have 3 sig figs, we have 4, 2, and 4. So this is going to give us 2 sig figs. And the rest of it is just simple multiplication division. I think you can handle that. This, just to show you as far as addition and subtraction, is one way I like to look at when adding samples or subtracting. It makes it easier to see sort of why we have different, how we deal with sig figs when adding and subtracting. 3 researchers using 3 different scales each determine the mass of a different sample of iron. If the 3 measurements are 22.3 grams, 0.12350 grams, and 199 grams, when they're combined, what's the total mass of this final sample? It helps me to understand this better to write these out in a column, and I line up the decimal points. And of course, we're adding all this together. And this lets us know where we need to round everything off. The first case, we're measuring to the nearest tenth of a gram. The second case, to the nearest 100,000th of a gram. Third case, to the nearest gram. So this has an error of plus or minus 0.05 grams. This has an error of plus or minus 0.00005 grams. This has an error of plus or minus 0.5 grams. And by error, put 0.5, easier to see. By error, I mean that's the error of that equipment that was used. So since this has such a big error, these other values are so precise, but their precision doesn't matter because of the error in that sample. So when we add these up together, our calculator will give us 0.5324 221 grams. We've got to round off. So I always just take our least precise value. You draw a dotted line down here to remind yourself everything after that has to be rounded off. So we get 221 grams will be our final answer. And that's it. Hopefully that helps a bit better on significant figures. And that leads to precision versus accuracy. Now, these terms are used synonymously a lot, but they really don't mean quite the same thing. Accuracy really is how closely does your measurement agree with the actual measurement. Again, getting to real equipment doesn't always measure as accurately as we would like it to. Looking at the darts over here on the side, these 3 darts are all very close to the bullseye, so they're all very accurate. So it represents 3 experiments that are close to the real value. If you assume the bullseye is the real value, that will be very accurate measurements. Precision really has to do with how closely do measurements agree with each other. In this second case, these 3 darts are very close to each other, but they're not close to the bullseye. So they're considered precise. Come back there. They're not close to the bullseye, so they're considered precise. They're close to each other, but they're not accurate. Which in real life isn't that big of a problem, because that's when we know we need to go calibrate our equipment. We can actually shift our equipment. We have their calibration settings. We take a known standard, bring it in, calibrate the equipment to make sure it's still going to be accurate and precise. Last case, we have 3 darts over here. I guess the errors earlier, but anyway, 3 darts that are nowhere near the correct value and nowhere near each other, so they don't have any accuracy or precision. Now, there are many cases where we'll take lots of measurements, average them out, and that will give us a more accurate value. We assume that we'll average out all the noise in the measurements, because it's hard to get the exact same measurement every time. But this is the difference between accuracy and precision. So precision often deals with, we think about like how many decimal places out do we carry our measurement. More precise instruments will measure out to more decimal places. More accurate instruments will also, that measurement will also be close to the true value. So again, for quantitative labs, every year, sometimes every month or every week for some labs, we recalibrate the equipment to make sure that it is actually measuring accurately and precisely. Precision is often inherent in the machinery, where accuracy may vary depending on the temperature, the humidity. That can all get the machine out of calibration, so it needs to be recalibrated. You might experience this when you go to like the old sets of bathroom scales. Before you get on the scales, if the dial isn't set to 0, you adjust the dial to set to 0, so you're actually you're resetting the accuracy of the scales. Then you get on the scales, measure your weight, get off again. And so that's really what you're doing, is calibrating the scales by re-zeroing that dial every time you get on the scales.